Researchers in quantum information often use a simplified diagram in order to talk about surface codes. It can be a little bit difficult for people who are beginners in the field to know exactly what's being discussed in terms of the number of physical qubits, number of logical qubits, and the distance of a surface code, given the diagram alone. So we're going to go over the calculation method quickly, just to see how everything works. Now, to start from the very basics, let's recall that x times z is equal to minus z times x, where x and z are the 2x2 Pauli matrices that we've been discussing throughout the course. We can very quickly, and if you're not following along, don't worry about it, we can define stabilizer codes to be a set of code states psi in the code C, such that s times psi is equal to psi for every operator s in a big S, which is a set of stabilizer operators. Right? So we say that S stabilizes psi because psi is the +1 eigenstate of S for all of the little s's in this big group of s's. And that's nice, and you can do a lot of classically efficient computations with this. But the really nice property is that this allows you to detect errors. Let's assume that, first off, each of these s's is going to be some multi-qubit Pauli operator, and that E, an error that may or may not have occurred, is also a multi-qubit Pauli operator. What happens if we try to measure S, and there's an E here that anti-commutes with S the same way X does with Z? If you go through this math for some specific example, or if you do it in general using only the fact that E times S is equal to minus S times E, and that E squared, like all multi-qubit Paulis, is the identity, you'll end up getting -1. Now, if this error had not occurred, right, not producing the state E psi, but rather psi, this would be +1. And this means that as long as we're working with a stabilizer code, errors are going to have a physically measurable effect on the system. So, how do we make a surface code? We begin with a square array of qubits that we lay out here, and then we start defining stabilizers. Here's a weight 2 stabilizer of the form ZZ on these 2 qubits. We have a weight 4 stabilizer of the form XXXX on these 4, and similarly, local stabilizers are defined all over the lattice. This arrangement of stabilizers and data qubits becomes this surface code picture, and typically people will include a little legend to let you know which of these letters corresponds to which of these colors, because it's not clear a priori. So here I've used black tiles to host Z stabilizers, and I've used white tiles to host X stabilizers. Here we can see the weight 2 stabilizers that are going around the perimeter, and the weight 4 stabilizers that are on the interior. The logical operators for this code run all the way over one side of the square or the other. Depending on which color is which, you might have different logical operators on different sides. But here, the logical Z operator runs down the right side of the tile, and the logical X operator runs across the top. And they're both weight 3, because we're dealing with a 3x3 square. How do you calculate n, k, and d for a surface code? N is simply the length in the x direction times the length in the z direction. So in this case, it's 3 times 3, which is 9. An important thing to remember is not to count the number of squares that are in a row, but rather the number of qubits that are in a row. So here we have 9 total. K, the number of logical qubits, is always 1 for these codes. There are some ways to get k not to be 1, but they are too advanced to cover in this course. And d, the code distance, is the minimum side length of this square, which is either Lx or Lz, whichever is smaller, the minimum, and in this case, that's 3. So as you can see, square tiles are nice when error rates are equal and you want to have equal distance for both x and z logical operators.